Bisection method. Here it is here, the bisection method. So this one. The bisection is regarded as the easiest of all the methods because any half-wit can take a range and bisect it. Bisect means cut it in half. Okay? So bisection method, everyone should be able to do the bisection method. And you're lucky because you're able to choose which method you solve the question in the test. And so if bisection method is the only method you can fully understand, then use the bisection method right throughout. You won't get excellence doing that, but you'll definitely be able to pass. So the bisection method works like this. We have a solution, this guy here, and we want to work out what that point is. We've got a function, which is y equals f of x, and it is wildly complicated and we can't solve it algebraically. So what we do with the bisection method is we start with 2 points. And we can call them all manner of things. Let's call them x1 and x2. Just 2 random points, and they're not that random. One has to be to the left-hand side of our solution, and one has to be to the right-hand side of our solution. And the bisection method basically says, let's guess the answer, and our guess is the midpoint of the 2. Simple as that. If you read about that thing last Friday when I wasn't here, you would have read the process, which is pretty basic. So x3, which is our first guess, is the midpoint, which is there. And we got that literally by finding the average of our 2 points, the mean. x3 is our first guess, and we could stop there, and it'd be a pretty shitty answer to the question, but it would be an answer, and that's called our first approximation. But what we then do is we say, well, okay, hold on. We substitute x3 into here and we get negative something, and it's not very close to 0. So we say, okay, let's have another guess. So we look at our situation and say, well, hold on. x3 is to the left-hand side of our answer. So let's now split x2 and x3. So we bisect x2 and x3, and we get that point there. We call that x4, funnily enough. And then we say, oh yeah, there's our second approximation, and it's now too far to the right of our answer. And so we then say, okay, let's split the region up, which we've now got between x3 and x4. So halfway between x3 and x4 is there. It's not a very good half, but so that midpoint is now, and you can basically see that, and anybody who is vaguely conscious, and even with a single figure age, I am almost certain of this, could appreciate that if I said, I've chosen a random position somewhere along the front here of the room, and it's somewhere between the door and the wall over here, or the filing cabinet, where do you think it is? Your first guess is going to be bang in the middle, because, I mean, why not? And I'll say, no, actually it's that way, pointing to the door. And then you go, okay, well, it's over here. And I say, oh, you've gone too far. So you know that it's between halfway and here, and your next guess is going to be here, and you are systematically halving and halving and halving the interval where the answer really is. Now, of course, as you said before, Jason, you're never going to get there unless you've got infinite amount of patience and you keep halving and halving and halving and halving, because you can keep adding on decimal points until you get to the quite a decent approximation of the answer. But it's going to take blimmin' ages. But the process, all you have to do is show that you understand the process of halving the interval. Now that is so basic that, you know, that's why it's a popular choice, because it's so easy to sort of intuitively understand, because that's how you would guess and check anyway. So the bisection method systematically cuts the interval in half, making sure that the true answer stays in the interval. Okay, it's quite hard to program on a spreadsheet, but that's what you do, and you don't have to obviously use a computer in the test. Next method, Newton-Raphson, P-H-S-O-N, Newton-Raphson method. This is far quicker, but a little bit more tricky. Newton-Raphson method, and we're going to do this as well, obviously, is that we take one starting point, and we call it normally x0 or x1. Okay? Newton-Raphson is something we're going to do, we're going to move on to probably, or you're going to move on to maybe on Wednesday, is you have one starting point, and Newton-Raphson method works like this. It says, okay, if our starting point is x0, let's go up to where, let's find out where the point is on the graph, which has x0. And then it does this. It creates a tangent, and that tangent there is not too bad for my tangents, but that's a better one. And what it does is it says, if we start at x0, let's create a tangent at the point where x0 is on your graph, and that tangent goes down, and where that tangent cuts the x-axis is my approximation. And so this point here becomes my first approximation. And then we go up to the line again. Second tangent does that, and you can actually see that in two goes here, the tangents swing in to the true answer very, very quickly. Okay, so the Newton-Raphson method uses a little bit of calculus, okay, which is why we do a little bit of calculus in this course, so that we're able to do the Newton-Raphson or understand the Newton-Raphson method. So these tangents zoom in and very, very quickly get the answer. For instance, this problem here, the bisection method one, it might take 10 or 12 goes to get within 1 or 2 dp, 10 or 12 cutting in half, because you're only halving the area. This will do the same job in about 3 or 4. So it's very, very fast, but it is, there are some issues with this, some graphs that cause it difficulties, but that's the Newton-Raphson. So those two methods we need to basically understand quite well, and it's not beyond any of us, because they are sort of geometrically quite straightforward. Okay?
Where the tangents
Across the x-axis.
yes,
That's your guess at the true answer. So x0 is your first guess. You just put a point out there somewhere. Then the tangent cuts at your next best guess, and then the next tangent, and the next tangent, and the tangents will get closer and closer and closer to the true answer. And each one is called an approximation. Now the last one was called, the last one that I'm going to show you is the secant method, and this has been dropped away about 10 years ago. But the secant method started off like the bisection method. It said, let's start with 2 points, x1 and x2, that surround the answer. And this is how we're going to get our next point. It worked out where we worked out where the points on the graph were, and then we connected the dots. And where the black line, which is called a secant, where the secant crossed the x-axis, that was your guess. Okay, so the secant method required you to be able to work out the secant, or the equation of the secant basically, it was in the formula, where between those 2 points, and where it cut became your first approximation. And then you made the same decisions as you made with the bisection method. You said, okay, this point here is to the left-hand side of the true answer, so I'm going to do the secant method on, I'm going to leave x2 where it was, x3, the point is there, there's my secant, it cuts there, there's my next point.
So there are quite a lot of ways of doing exactly the same stuff.
What's that?
Quite a few ways of doing exactly.
Absolutely, yeah. These are all different methods. And there's another method called false position, and I still can't remember that one. I was probably taught it. Well, it's not trial and error. It's just a system that you could actually use, which, as I say, your calculator does, to repeat and repeat and repeat. You could program a spreadsheet or a computer to literally repeat this process over and over again, and it'll eventually zoom in on the answer completely manually without any algebra, because there's no algebra to be used. And your calculator, and machines are good at this because machines process very, very quickly, and your calculator, when you ask it to solve something, it says, it basically uses, I don't know if it uses bisection method, but I think it uses I think it uses Newton-Raphson, in fact, to iterate, which means repeat the process over and over and over, but it does it in the blink of an eye because you push the button and it comes up with the answer. You think, oh, it just works it out. Well, actually, it's done 30 or 40 different repetitions and zoomed in on an 8 dp answer, and it's all done it in 0.1 of a second. So, but it's still doing it manually. It's not, your calculator can't do algebra. Every time it solves a problem, it's doing a numerical process to do it. Okay? It just does it so quickly that you think it's bloody clever. It's not that clever at all, really. It's just good at repetition. So this guy down the bottom here, the secant method, was abandoned because although it was, it was just another way of doing the same thing, the formula required here was so complicated that people were ballsing it up at the formula stage and not getting the correct answer far too often, and it was sort of testing the wrong thing. So these two methods, the one that we have to worry about, the Newton-Raphson and the bisection, are both quite straightforward and allows you to actually be tested on the right process, which is the numerical methods. So by the end of this term, comfortably by the end of this term, we will have sussed both of these to excellence. And excellence is actually very easy. This section is very, very easy for excellence. It's about describing what would happen if the graph was like this and you started here and you did this and that and so on. You can geometrically, all of you can geometrically see what's going to happen. For instance, if I said we're going to use Newton-Raphson to work out that solution on that graph, and my starting point's going to be here. What's going to happen? How does Newton-Raphson work? Answer, it requires tangents to your graph. If my starting point is here, what's the tangent to this point? Yeah, my first tangent does that. Never touches the x-axis. Your formula craps out. You get no answer. That's bad. Okay? Whereas if we started with two points x, that's no good. If we started with bisection method with the point x0 and x1 over here, no longer worried about that guy, then we will be guaranteed with the halving and halving and halving method of the bisection method that we will eventually get to there. The downside of that is what? Takes bloody ages. In fact, it'll take you half an hour when you set out the table and you do it. It'll take blooming ages, but you will get there. Newton-Raphson method, very fast, but if you start in the wrong place, you could get nothing. Yeah. No, definitely not. You'll never be asked to do the whole thing to 8 dp. You'll be asked to do it to you'll be told, do this till you're confident to 1 or 2 dp. Something really short, you only have to do it sort of 4 or 5 times. So excellence is about discussing geometrically what can happen in different situations and what the downfall is of, say, using Newton-Raphson. We know what the downfall is of bisection. It just takes ages. But you will get the answer. Newton-Raphson is really fast, but sometimes no good. If this happens, that's bad. Okay? Or you might start here, and your first tangent does that, and your second tangent does that. We will look at that later on. Okay, that looks a bit of a mess, but it did make sense when I wrote it. Okay, so that is a potted summary of the whole thing. And we will look at some more of this later.